Okay, in this unit we're going to look at host security, and especially around the usage of the TPM chip and the Apple T2 chip. We'll then look at a little bit of disk encryption around BitLocker, TrueCrypt, and then at the end we'll look at Entropy to see if we can actually detect when something is encrypted. Okay, so here's what we have. We have our choice of operating systems, Linux, Mac OS. You may trust one over the other, but we need to make sure that at least the computer boots up into some well-defined state. So the last thing that we want is for anything, a piece of malware, to be able to interfere with the boot process and load some malicious code. So a good part of what we want for our host security is that the computer starts up in a well-known state. So this typically involves the BIOS initializing the hardware, and then the BIOS calls the master boot record. We then load the code that's on that on the boot sector of the active partition, and run the code and start up the operating system. So that's the standard way that we boot a computer up. So let's look at the TPM chip. TPM chip is typically used within Windows laptops, not as much on Linux, and certainly not inside Mac OS. So within it we have typically this chip here. This is the TPM 1.2. So TPM 1.2 supported RSA, SHA-1, and so on, where TPM 2.0 supports elliptic curve cryptography, SHA-256, and so on. So it's a definite upgrade in terms of the cryptography that's actually used inside the device. It has a very basic crypto processor, so it's not a processor that is going to do anything at scale, but it can certainly calculate signatures and so on, and define the trustworthiness of signatures. In here too we have registers. So these registers make sure that when the computer is booted up, then it is booted up within a trustworthy state. Along with that, we have persistent memory, and the two most important key pairs are the endorsement key, or AK, and the storage root key, or SRK. The endorsement key is a key pair where the private key is not released to anyone, but the public key is available. And this is the key that is stored long-term in the device. The storage root key is often used to encrypt disks and will be changed every time there is a new user of a computer, or when the system is scrubbed. So our key focus is to make sure that the platform, there's platform integrity, that it boots up into a known state. There is disk encryption through the usage of keys, and there is also some password protection on the users. There is some protection of the user's password on the system. So the endorsement key is important because when the computer is manufactured, then a key pair is created. Typically this will be an RSA key, or it might increasingly be an elliptic curve key pair. So with this, what we can do is that we can release the public key to anyone who wants to send a secret message to the computer, and then they will encrypt with the public key, and then only the private key can actually decrypt the message coming back. In this way, we have a trustworthy source of encrypted data. The other thing that's used for is to identify the computer to the manufacturer or through some sort of trust infrastructure. With this, what happens is that when the computer is made, there is an endorsement key certificate say from the Alice Computers Limited, will create this endorsement key certificate. And inside this, there will be the public key of the computer. The key pair is then put on the machine, and we get rid of the private key. Then, when the computer wants to identify itself as still being the same computer, it will take the private key from the key pair, from the AK key pair, and then encrypt a message such as the serial number or the name of the computer with the private key of the EK. That's then sent here, and then the manufacturer will look at the public key and be able to decrypt the signature and check that it's a valid message. In this way, the endorsement key makes sure that the computer is still the computer that it is. And we can do this for any electronic device if we fit a TPM and we have endorsement keys. The manufacturer can still check to see if it's still the same device. Unfortunately, it is possible to desolder the chip and put it onto another computer, and that can cause a flaw. The other one that we have is the storage root key, or the SRK. With this, again, we have a key pair, but it's created by the owner of the computer. We can use TPM utilities such as these ones to be able to examine the public key and to create new keys. But we should only be able to reveal the public key part of it. What typically happens is that we will take the AES key, which is going to be used to decrypt the disks, and encrypt and decrypt the disks, but we will protect it with the public key of the SRK pair. Then only the private key can actually, the associated private key of this key pair can decrypt this encrypted key to release the key which is used for the encryption. Obviously, we would never use RSA or elliptic curve encryption to actually encrypt drives because of the performance issues, but AES is a good method for this, and we'll use our key pair to protect the key. Unfortunately, Rocca came along, and Rocca was a vulnerability that was caused by the generation of weak RSA prime numbers. It's identified with the CV number, and it's called the return of the Coppersmith attack. So it was possible to be able to determine the private key given the public key. And you can try this little example here. Should work, where we can actually determine a prime number from a set of values. Okay, the basic principle behind it is this, and this is a very simple Python program to be able to determine the prime number. And what happened? A paper was published that showed that these TPM 1.2 chips from a certain manufacturer were weak. You can see here that 512-bit RSA keys could be cracked with at the cost of less than a cent in terms of cracking on this Intel infrastructure in the cloud. 1024-bit keys cost a little bit more. It's about nearly $2 for every key. But obviously when we went up to 2K, then it was nearly $1,000, and then 3K and 4K keys have massive costs. So you could say that anything in this region here was probably crackable, certainly for certain individuals. Anything above, it will become much more costly And we can see the amount of time it takes vastly increases as we go up there. So that's probably the reason that we're using 2K keys for RSA, and if we can, 4K keys, or move to elliptic curve. In terms of the vulnerability, it's fairly easy to crack the TLS and PGP. There was some problems with forged certificates and with code signing. Code signing is a particular problem in that you end up not trusting a whole range of software. So the evaluation was this, and it was the Estonian EID system that was seen to be highly vulnerable because the public keys were actually published online. Over 50% of the keys online were vulnerable, and in some cases it was 100% for the Estonian e-residence system. Estonia, though, moved ahead and migrated from these static keys towards a mobile device solution, which allowed for the upgrade of the keys to a more secure infrastructure. So let's see how Apple do this. So you won't really find a TPM chip on an Apple computer. What you'll find is this T2 chip, and it's a wonderful little chip. You'll find it in controller, and you can see if you have a T2 chip, if you have an Apple device there. It does lots of things, so it's not just for security, but it will do generally the core grunt work with inside the computer. It does a lot of the audio processing, video, image processing, and so on. But a core part of what it does is to be able to encrypt from the SSD to the processor. And we have fast DMA memory access to be able to take encrypted data here and feed it to the processor. And how this happens is that there is a secure enclave processor inside the T2 chip, which makes sure that the key that's used for the encryption, the AES key, is kept secure so that no one can actually access this key. It also supports the Touch ID inside the Apple Mac, and also the fingerprint data. So this is obviously important on the device, because the last thing that Apple want is for an intruder to be able to get access to the Touch ID information and also the fingerprint information. The other thing it does is that when the lid of the computer is closed, then it disables the microphone. Along with that, it looks at secure encrypted file storage with File Vault, and secures the boot process. The way that it's created is there's a unique ID created, and it's a 256-bit AES key, and it's burnt into the device when it's manufactured. It cannot be revealed through any JTAG enablement or through debug interfaces, and so it can be seen as secure. It also does the lockout. So as many people will know, the iPad, iPhone and Apple will lock you out after a certain number of incorrect password attempts, and this increases the trust from the user point of view in the security of the device, but can also cause problems in that it is actually almost impossible to unlock this process. So let's look at disk encryption. So the number one system in disk encryption is BitLocker, and is used by many corporations to encrypt data onto the disk. But there is also other packages that are possible in McAfee, Sophos, Symantec, Checkpoint, and so on. But the two main ones are BitLocker and what used to be called TrueCrypt. So this is an open source, where this one is a closed source package. And what we can do is either encrypt the whole disk, which is much more secure, or we can encrypt individual files or folders. So within our organizations, we typically define a FIPS level. In the FIPS level, as we go up, we start to create isolation barriers between our identity infrastructure and our back-end security. So if we go right up to FIPS level 4, we have physical security methods and also robustness against environmental attacks, such as power supply failures. So the ways we can do this is, obviously, if we're using encryption, we need a fairly simple method, if we can, to be able to encrypt the disk, but it's got to be secure against attack. So the ways that we can do it is that we can have a password or a passphrase to be able to open up the key that's used for the encryption. We can have a USB drive that contains the encryption key, so that when we mount it, the encryption key is loaded. We can have one-time password systems that we can look at the ID or the one-time password and then feed that into our computer and open up the drives. Or we can have biometric devices where we can integrate fingerprint readers and things like that. Along with this, we also can have multi-factor, that we can have 2 or more of these factors all working together to be able to secure the system. Okay, so we can have this EFS in Windows. We can have this method here, which is fairly not a great method, but we can encrypt the drives or folders with encryption. But to do it properly, we look at BitLocker encryption of a whole volume. So with this, we have a boot drive, which is an encrypted, and then that will lead to an encrypted drive. So obviously this is very important. If this doesn't start up, then we're going to have problems actually mounting the encrypted drive. So we run this off the TPM module, and this contains the encryption keys and a bit of the operating system loader code that will boot up the device. We can also have a user authentication mode to link it to things like Active Directory. And we can also use keys, where we can insert a key to be able to boot up the computer in a trustworthy way. The EFS system is fairly simple in its operation and can encrypt a folder. So anything that you right click and then encrypt the folder, anything that's stored in that folder is then encrypted. The way it works is that we take an encryption key, a random one, typically 256-bit AES. We will then create a key pair, and the public key then encrypts the key that we're using for our disk. Then we can then read that key using the private key from the certificate and open it up, and we have the encryption key for the disk. So this shows an example of the certificate that's created. If we lose the certificate, then we won't be able to decrypt our files. So in this way, we can see it's a certificate for the encrypted file system, and then it has the public key pair on it. So in this case, it's there's a signature in there, and the issuer is the person, the user on the computer. So no one else should be able to get access to this certificate. Okay, so it's a good idea to keep a backup and to have a SIR file that is kept as a backup, and we can also have the PFX file to be able to store that on a USB drive just in case we lose the certificate or the boot on the machine. So you can export that onto that file. Once it's encrypted, we can use the cipher command on our folders, and it should give us an idea of who owns it and then what the encryption is used. So we can see here it's AES and there's no recovery certificate from there. And then if we want to be able to export our certificate, then we use the /r command option there with the cipher, and it will export 2 certificate files for us. We would then put these onto a USB drive or an SD card, just in case we have to recover them again. Okay, so there's the example there, where it's exporting the, or it has, this is the thumbprint of the certificate here. And here is the export of the certificates for this file here. The other open source system that's now called VeryCrypt is called TrueCrypt. And TrueCrypt takes a different approach. It's open source. And what we have is a password and a salt value. It goes into PBKTFS2 and generates a key. That key is then used to open up a header which contains all the keys that we require and the definition of the keys inside the header file, and then we can decrypt a volume. The volume is added as a file, so it's a TC file, and we can mount that as a volume on our drive. We can use many different encryption methods if we want here, and also different hashing algorithms from here. But typically we'll use AES for that. Okay, so we initially create a volume. We define the size of the volume, define its encryption type that we're going to use, and then we can mount it onto our system as a drive. Okay, so we take our TC file, we perhaps store it onto our system, in this case in the C drive, select it, and then we mount it as a drive. So the user would see it either as a Linux volume mount, or in Windows as one of these drive volumes here, and we can then use it. We would then dismount the drive at the end of it, and it will save anything to that we've created into the TC file. Okay, before we create our volume, we can do a quick check to see how fast it is. You can see we've got hardware accelerated here, and we get fairly good throughput times for AES. But when we go down here, if we use Serpent to fish AES, then it's much slower. Of course, because we're using overlay encryption. Okay, so that's the method. It's just a simple password. So that can be weak, so we can use a cracker here to be able to try different passwords. But because we're using PBKDFS2, it's a very slow process to be able to generate the key. So we can't really do this at scale from the password. So it's fairly secure in its operation. So that's the basic hashing methods, and also for the symmetric key methods that we're using. So TrueCrypt was open source for a while, and unfortunately this happened. So something didn't quite go right, and the team developing TrueCrypt defined that everyone should move to BitLocker, which was a bit strange because before this they were saying that TrueCrypt is a replacement for BitLocker. So maybe they found a code bug, or there was a binary code exploitation. No one quite knows yet, but it was closed down. This was the web page that was created from it. But then many have defined that it should continue, and the source code moved outside the US to Switzerland, and now new initiatives are porting it onto new systems, and the most recent is called the Vericrypt. This was interesting because recently there was a bug found on the SSDs, I think it was Samsung SSDs, where it's found that hardware encryption wasn't actually being enabled, which meant that many BitLocker implementations weren't actually encrypting the data onto the disk. At the time, many security analysts were saying that users should either enable software encryption for BitLocker or to go for Vericrypt, which does use software encryption. Okay, so that's been an outline of the two main disk encryption methods. Let's look at last little bit, which is entropy. So entropy is a way for us to determine whether something is encrypted or not. So if we see a file on our network and we do a quick check of it, and what we do is we measure the Shannon entropy. So the Shannon entropy is the minimum number of bytes that are represented for each byte character. So it's a measure of the amount of information inside the bits, inside the bytes. If we have totally random bytes, then each byte is evenly distributed, and no byte is more common than another. So the maximum we can get for a Shannon entropy is 8 bits per byte. So we can see here this is almost 8, so it looks like this file has been encrypted, and it has, because it's a TC file. It's a TrueCrypt volume. For this one here, we can see here this is for a compressed file. So a compressed file is like a docx or a zip file. We can see 7.987 is nearly 8. So that looks as if it's either encrypted or compressed. In this case, I think it's compressed. If we take a doc file, we can see here for the doc file, then we only get 4.64. So this isn't compressed, or it isn't encrypted. So got a little tester here. Obviously, the more bytes that we get, the better we can actually measure this. But if I take these 10 bytes, we can order in terms of the frequency of each, and then we can actually measure the randomness of it. So if I take a TrueCrypt volume, such as this one, this is the bytes I've taken from TrueCrypt. From here, the first 256 bytes or so, and then I put it through, and then we can determine the Shannon value of 7.13. So I haven't really taken enough bytes to be able to get it to 8, but you can see here it's pretty much near that 8 value, so it does look as if this could be encrypted or not. So all I'm doing here is taking the frequencies of the bytes, laying them out, and then I do some little bit of maths just to add them all up and take log to the base 2, and I can determine that. So anything that's around 8 looks as if it's either encrypted or compressed. If I try a pkzip file, pkzip, you notice here by starting with these 2 bytes. So I could probably check that this was a zip file anyway by looking at that and then the bit that comes after it. But somebody could change those 2 bytes and then try and hide this into a PowerPoint slide or something like that. So you can see in this case we're getting an entropy value of 87.7%, and it's over 7 bits per character. So that definitely looks to be either compressed or encrypted. If I try this one here, there we go. So you can see here that's given us an efficiency of 50% for that. Okay, so in this way we can actually detect if something is encrypted or not. We can look at volume, we can look at files, folders, and so on. We do a quick check of the bytes, lay them out in terms of the frequency, and then we can determine the Shannon entropy. Anything above 7 is something that looks to be either encrypted or compressed. Okay, so here's an example here. There's our PK-zip file. When we look at it, when we look at our file encryption file, and we illustrate in terms of the intensity of each of the, in a grayscale, this is what it looks like. So an encrypted file, when visualized, just looks like random noise. Okay, so that's been a coverage of some host-based security. We looked at TPM and secure enclaves, then on to BitLocker and TrueCrypt, and then finally we looked at Entropy inside our systems. Okay, thank you.